What specific problem does the proposed method aim to solve based on the student's paper?
The proposed method aims to solve the problem of improving the performance and generalization of large language models, LLMs, in math reasoning tasks by utilizing synthetic data. Specifically, the method focuses on understanding the impact of synthetic data, both positive and negative, on the behavior of LLMs during training. The goal is to address issues such as amplifying biases, misinformation, undesired stylistic properties, and overfitting that can occur when training solely on positive synthetic data. By carefully constructing negative synthetic data and emphasizing critical steps in the reasoning process, the method enables per-step credit assignment, which leads to improved model generalization and performance. The study aims to provide insights into how synthetic data can be effectively used to enhance LLM capabilities in math reasoning tasks, ultimately aiming to overcome the limitations associated with training solely on expert data or positive synthetic data.
How does the proposed method or algorithm work? Illustrate step by step.
The proposed method works by utilizing synthetic data, both positive and negative, to improve the performance of language models in math reasoning tasks. The process begins by generating synthetic data consisting of problems and corresponding solution traces from highly capable models like GPT-4 and Gemini 5 Pro. The synthetic data is then used to train the model through supervised and rejection fine-tuning, SFT and RFT methods. SFT involves training the model on positive synthetic data to maximize the likelihood of the next token given all previous tokens. On the other hand, RFT involves training on both positive and negative synthetic data pairs to contrast good and bad choices for critical intermediate steps in the reasoning process. The method also incorporates direct preference optimization, DPO, to leverage negative synthetic data generated by the model. By carefully constructing negative data that emphasizes critical steps, the model can unlearn spurious correlations and improve performance. The conceptual model introduced in the paper explains how training on negative data enables per-step credit assignment, which is crucial for identifying and emphasizing important decision-making points in the reasoning process. Furthermore, the method involves calculating advantages for each step in a response, which helps in characterizing critical steps that need to be generated more precisely. By using advantage-weighted reinforcement learning, the model can effectively learn from both positive and negative synthetic data, leading to improved generalization and performance. The approach of per-step DPO is shown to be equivalent to advantage-weighted RL, which aids in better credit assignment and decision-making during the training process. Overall, the proposed method works by strategically incorporating synthetic data, both positive and negative, to train the language model on math reasoning tasks. By emphasizing critical steps, unlearning spurious correlations, and utilizing advantage-weighted RL, the model can improve its performance and generalization capabilities significantly.
What are the theoretical or practical benefits of using the proposed method, according to the paper?
The theoretical benefits of using the proposed method in the paper include the ability to perform per-step credit assignment, which helps in identifying critical steps over irrelevant or incorrect ones by computing advantage estimates. This method enables the model to improve test performance and scaling trends over traditional supervised fine-tuning, SFT, and standard direct preference optimization, DPO, with the same data. Practically, the proposed method of per-step DPO allows for more efficient training on synthetic data, leading to a significant improvement in model performance equivalent to scaling up the positive data by 8 times. Additionally, the conceptual model of using negatives for credit assignment helps in unlearning spurious correlations that may arise from training on positive data alone, thereby enhancing model generalization and mitigating the risk of overfitting on irrelevant or incorrect steps. The method also provides a framework for understanding and addressing failure modes of training on positive data, offering a more effective way to leverage synthetic data for improving language model reasoning capabilities.
How is the proposed method validated or tested based on the student's paper?
The proposed method is validated and tested based on the student's paper through a series of experiments and analyses. The paper presents scaling results for both positive and negative synthetic data on math reasoning benchmarks, such as GSM-8K and math. The experiments involve fine-tuning models on varying sizes of synthetic data, comparing performance improvements, and observing scaling trends. The results show that training on negative data, specifically using per-step direct preference optimization (DPO), leads to consistent performance gains beyond supervised fine-tuning (SFT) and rejection fine-tuning (RFT). The paper also discusses the importance of constructing negative data carefully to enable per-step credit assignment, which is validated through empirical results showing improved model generalization and suppression of irrelevant or incorrect steps in responses. Additionally, the paper provides theoretical explanations, such as the equivalence of per-step DPO to advantage-weighted reinforcement learning, RL, to support the observed performance improvements. The experiments demonstrate that training with negative data can significantly enhance model performance, leading to a sample efficiency improvement equivalent to scaling up positive data by 8 times. The paper also compares different approaches to pairing positive and negative responses, showing that the choice of negative data significantly impacts model performance, with per-step DPO outperforming standard DPO and random pairing methods. Overall, the validation and testing of the proposed method in the paper are based on rigorous experimentation, theoretical analysis, and empirical results, showcasing the effectiveness of training on synthetic negative data for improving model generalization and performance in math reasoning tasks.
What results were achieved with this new method as presented in the paper?
The new method presented in the paper achieved significant results in improving the performance of language models on math reasoning tasks using synthetic data. Specifically, the study found that training on negative synthetic data, in addition to positive data, led to substantial performance improvements. The method of per-step direct preference optimization, DPO, was able to address the limitations of training only on positive data by enabling per-step credit assignment. This approach resulted in performance boosts equivalent to scaling up positive data by 8 times. The study also showed that training on negative data helped in unlearning spurious correlations and improving model generalization. Additionally, the method of per-step DPO outperformed standard DPO and rejection fine-tuning (RFT) approaches, showcasing the effectiveness of this new method in improving model performance and sample efficiency. Overall, the results demonstrated the utility of negative synthetic data in enhancing model capabilities and addressing the challenges associated with training on synthetic data for math reasoning tasks.
What are the limitations or drawbacks of the proposed method highlighted in the student's paper?
The limitations or drawbacks of the proposed method highlighted in the student's paper include the following. 1. Verification challenges. The paper mentions that verification of high-quality math data can be challenging, as it can be hard to ensure the accuracy of the synthetic data generated by larger models. This implies that there may be difficulties in ensuring the correctness of the synthetic data used for training the models. 2. Spurious correlations. Training on positive synthetic data alone can lead to the amplification of spurious correlations, especially if the data contains incorrect or irrelevant intermediate steps. This can result in the model overfitting on these spurious correlations, leading to a decrease in performance or even model collapse. 3. Causal confusion. The paper discusses the issue of causal confusion in imitation learning, where the model may develop incorrect causal associations between spurious steps and valid steps in the solution. This can lead to incorrect decision-making by the model during training. 4. Performance plateau. Scaling up negative data for training may lead to performance saturation or even a decrease in performance, as seen in the results presented in the paper. This indicates that there may be limits to the effectiveness of using negative data for training the models. 5. Complexity of pairing. The paper mentions that the choice of negative data pairs for direct preference optimization, DPO, can significantly impact the performance. Standard pairing of positive and negative responses may not always lead to performance improvements, and alternative pairing strategies may require tuning parameters to avoid performance degradation. 6. Edit distance pairing. Even when pairing positives and negatives based on the highest edit distance, there may still be limitations in improving performance compared to methods that consider per-step credit assignment. This suggests that the method may still have room for improvement in effectively utilizing negative data. In summary, the proposed method in the student's paper has limitations related to verification challenges, the risk of spurious correlations, issues with causal confusion, potential performance plateaus, complexities in pairing positive and negative data, and the need for further optimization in pairing strategies.